So some of the larger objects here will start to attract other objects nearby. They start to clump up, and you start to get a conglomeration going. And as more objects clump up, they have higher gravity, they pull more stuff into them, and it's exactly the same process as you were talking about, the formation of the Earth. That's how pretty much everything solid in the universe got started. It just kind of fell together from density variations in clouds of what have you, be it gas, dust, rock, snow. And the sedimentation effect then takes over in the case of Saturn. And Cassini has images of these new moons being formed, like, you know, the size of an apartment building or something, where these clumps of snow have collected more mass, and because of that, they're getting pushed out by the forces of all of the smaller material around them. They get pushed up to the edge of the rings, and they get put out at the edge. It's like occasionally a moon just gets spat out, and they just orbit around the edges of the ring.
So I
plane.
just have a question then. If say they're now thinking that the moon wasn't a product of the Earth. Or
No, they're not thinking that. It definitely was.
All right.
Yeah.
Okay. All right. That's okay. Yeah.
So I was.
was.
You're okay.
I just want to say, well, where did it come from if it wasn't Earth?
I'm about to circle back to that with this analogy, because at the edge of that ring system, then you have a bunch of these comparatively large chunks, and in the early solar system, you had a lot of what are called planetesimals, basically baby planets, that were all rocking around and crashing into each other and forming into larger planets or breaking apart into asteroid fields. It was chaos. It was really, really energetic environment. And you had the young Earth, similar to one of these little chunks that had been ejected, recently formed, and then another chunk came along and collided. And one of two things is going to happen when two chunks collide. They're either going to both smash apart, or they're going to break each other up and then reform. And in the case of the Earth, the current prevailing theory is that another planet, or planetesimal, which has been named Theia, even though it doesn't exist anymore for us to go, there it is, impacted the Earth at kind of a glancing blow, and that destroyed Theia, and most of the material of Theia fell into the Earth, but because it was a glancing blow, a good chunk of Earth and a bit of Theia were smacked off, and that would have formed a ring around the Earth, as in Borna's question earlier, which then coalesced into the moon. That's the current thinking. There's actually
Is that where water came from?
So water is thought to be a comet import, as in, so
We didn't make it.
as far as I'm aware, no.
You can't make water.
I mean, you can in terms of nuclear physics. You can fuse molecules together and make H2O. But so in the early solar system, the stuff of the planets was pretty much evenly distributed. I suppose this would be before you could call it a solar system, when the sun was just starting to kind of form. There was this evenly distributed cloud of stuff. And as the heavier stuff started pulling more on the lighter stuff, it would have collected in the center. The rotation started, you got sedimentation going, you have sort of layers, just like the rings of Saturn, you'd have layers of rocky material, and then further out you'd have layers of lighter material, other way around. But anyway, it would be separated out. So there would have been probably a ring of just like water, because it would tend to come in a certain size and shape and weight, so it would sediment out as well. And that coalesced into comets. And we still have comets that are as old as the solar system. It's 4.5 billion years. Get knocked out of their orbits at the extreme edge of the solar system. I can show you actually on this where they are. It's thought that with the chaos of the early solar system, comets were getting knocked into the inner solar system quite a lot and delivering that primordial water to the inner planets. Now, why did Earth get so much of it compared to everywhere else? Even that question is a little bit complicated, because it's not that much more than everywhere else, to be honest. I'll turn on comets now. Everything's going to get a bit hairy because there are a lot of comets. Let's see, where are we? Now, so this is all the comets that we know of at the moment. But you'll notice that they all kind of share something in common. They're all going in and past the sun. So if we concentrate on one, so there's one here, right? That's a fairly clear shape there. It's an oval shape of the orbit. So that comet, most of these will have recently passed the sun, because the period of time it takes for them to complete these is very long. What we're actually looking at here is an observational bias. And what that means is that we only see the things that we've actually seen. So what this indicates to us, this sort of shape, is that there's a couple of different populations of comets at different distances from the sun. You can see quite a few of the orbits terminate at this kind of range, and then as we go further out, there's another sort of this range here, and then further out, another here, and then further out here. So there's multiple sort of shells, if you will, of comets orbiting the sun. And most of those comets will be in circular orbits that never come into the inner solar system, so we never see them. So they're not here in this simulation, because this is only what's known. So we can imply, or infer rather, from the origin point, I suppose, of these comets, where they came from. So these are the leftovers of the water that was sedimented out towards the outer edge of the solar system. And as collisions with the inner planets cause changes in gravity, or perhaps, over the 4.5 billion years of the solar system's existence, we have orbited the center of the Milky Way. I can't do maths that quickly, but we've orbited it many times. It takes about 150 million years for us to orbit the center of the Milky Way, so if anyone can work that out, but it's more than 10 anyway. And every other star in the galaxy is orbiting the center of the Milky Way as well, but every star is pulling on every other star, so the orbit of a star around the Milky Way is kind of wobbly. And you're going to have stars getting close to one another and pulling on each other and pulling on the planets and pulling on the comets. And it might be just a subtle nudge, or it might be a fairly energetic slingshot that they give them. And so a lot of these comets that are coming in and saying hello, they may have done that 20, 30, however many times, thousands of times, since whatever disturbance it was knocked them out of their nice circular orbit around the sun. And that's been happening since the early formation of the solar system. So when things were crazy back then, a lot of those were going to come in, and because the center of the solar system was just full of planets and rocks and asteroids and clouds and stuff, they were going to get slowed down, they were maybe going to hit stuff, and they were going to deposit the water that they're all made of on the inner planets. So that doesn't necessarily answer why Earth is so much more than, say, Mars.
Can I just about the wobbling bit,
Sorry?
You said, about wobbling?
Yeah, sure.
My understanding is, just getting back to Earth.
Yeah?
And the analogy about baby moon out
Yeah.
there. Like all offspring, they want to move away. and is it true that the moon is moving away, and that there is a danger that it will, because of the gravitational hold,
Yeah.
it will be disturbed, and so therefore the Earth might start to wobble a bit.
Yes. Yeah, that's true actually. But like many of these kind of scary sounding concepts in space science, this will play out over an extremely long period of time. So The moon is moving away from the Earth
Yeah.
at a rate of maybe a centimetre per year. And that rate varies over time as well. Like it's chaotic in itself, so it's not a constant. Because if you extrapolate that out, it's like, oh, it's only X millions of years left. But no, it's been sort of jittering a little bit over the eons. But yes, your query about the Earth wobbling is very astute. The moon is thought to exert a stabilizing influence on the Earth's axial tilt. So the axial tilt is, I can't remember how to turn that on, but if we go around where we can actually see some detail on the Earth. So poles are weirdly ice-free in this, but if you imagine a line sticking out of the North Pole and out of the South Pole, that line is the axis around which the Earth rotates. And the moon going around helps to keep that axis pointing in its correct direction. Now, it does actually wobble a little on its own, but it's a predictable cycle. Mars, which we haven't visited yet, is a good example of a planet that doesn't have a massive moon like Earth does, and suffers, oh yeah, I forgot I turned on comments, suffers from the axial wobble problem. So again, it's over incredibly long time scales, but is that Mars? Yes. I was going to head back to Venus there, thinking it was Mars because of the way it looked there. But anyway, so here's Mars, looking gorgeous. And over the lifetime of Mars, there's evidence in the rock core samples that have been drilled by NASA and Europe's rovers, and China's rovers for that matter, that so rock kind of keeps a magnetic memory in it, if you will. It's a little bit complex, but magnetic minerals in the rock will have certain directions that they face, and they kind of get locked into that. So you can use rock as like a time capsule for what direction magnetic fields we're pointing in. And the magnetic fields on Mars, it doesn't have an overall magnetic field like we do that keeps us safe from the sun's rays, but it has localized little umbrellas of magnetic fields. And they get pushed around by the solar wind. And so you can actually see from what angle the solar wind was coming in these rock samples. And that indicates that over the lifetime of this planet, its axis on which it rotates has just kind of wobbled very wildly. I think it's like 40 degrees of difference over the course of its lifetime. And that's thought to be because it doesn't have the stabilizing influence of the moon like we have. Now, I don't think, well, I know we certainly don't need to worry about the moon leaving us anytime soon.
We won't be around anyway.
Well, you and I, maybe not. But hopefully humanity will. Yeah. So, where should we go from here, dude?
So
Yeah.
I mean, I know it's a very general question, right? But the whole thing of climate influence in the life we live.
Yeah.
Consider what you've shown us here tonight, like
Yeah.
in terms of like trajectory of time. It's, you know, how much is human influence got to do with? It's kind of minute, really, isn't it?
It is a different topic, but
I know it's difficult.
yeah,
I mean,
like there are climate factors and there's the factor of not climate factor, but like axial tilt factors that affect the climate. There are factors of difference in the sun's output. Over the course of its lifetime, the sun can get brighter and dimmer. One of the ice ages, or probably more than one.
the planet will survive regardless.
Yeah, but the thing...
There might be any humans on it.
That's true. That's absolutely true. The planet will always adapt, and nature in general will always adapt, save for devastating things like another Theia impact. Life would not survive that. But what's different now, so when you look at the history of changes in the climate on planet Earth, one of the most drastic changes in the fossil record, I think was called the Ordovician extinction event. And I'd only be guessing at trying to recall how long ago that was, but it was something on the order of 1 billion years ago. And I think 60% of all life on Earth died out. And the cause of that was a rise in carbon dioxide levels that was somewhat equivalent to what's happening at the moment. The carbon dioxide levels are going up. The difference in that event was that that rise occurred over the course of something like 40,000 years. And now it's occurred over the course of 80. So there's no natural phenomenon that has done that in the history of the Earth at the speed that it's happening now. And there are markers in the chemistry of the carbon in the atmosphere that indicate that that's carbon produced by human activity. So I'm quite convinced that the problems we're having now are our own doing.
Could you explain the term solar winds? You happen to mention it. In
Sure.
passing.
Yeah, great question. Let's see. So we're going to look at the sun, which I don't recommend doing in real life. And actually, I will do this. Yeah. Let's turn up the exposure because this this simulation does actually model solar winds. Yeah, perfect. Okay, that's too much. So if I increase the time speed here, no. Yeah. So that's I think 10,000 times faster than normal. And so what we're seeing here, this kind of flame-like effect, that's the sun essentially burping. So the sun is a gigantic ball of superheated plasma. And what that means is it's a big ball of fire. It came together in the same way that the Earth formed, that those little snowballs formed around Saturn, the same process. It started out as a big nebula cloud, and I'll show you what those look like in a moment because they're beautiful. And somewhere in the cloud there was just a little bit more gas than in the surrounding regions, and that gas had a little bit more gravity, and that pulled in neighbouring gas, and that gas became heavier and had more gravity, and so it pulled in more gas. Over and over it goes. The gas collects. It forms a protostellar disk, is what it's called. This big whirling mass. Again, I can show you in a moment of material, and all of that material has differing levels of electric charge. Electric charge produces magnetic fields. And when you collide all of that material together, and we're fast forwarding a lot, but collide it all together, make a star, those magnetic fields and electric charges don't go away. They stay there. And the star is undergoing nuclear fusion at its core, which is creating a lot of heat that's pulsing up through the star. And as you know from watching your kettle boil, steam rises because it's hot. Heat makes matter rise through a gravitational field. And that rising matter next to less hot matter that's not rising, both of which are magnetically charged, they're going to stir each other around. And so the sun is an enormous tangled ball of magnetic fields. And those magnetic fields are made of so much combined matter that they're insanely strong. And as that material gets churned and twisted and stirred around itself, those magnetic fields are interacting in similar ways. And they will sometimes snap off one another. And when they snap, they carry some of that electrically charged material with them and throw it into space. And so what we're seeing here is material that was inside the sun getting flung out by those snapping magnetic fields, by the churning of the nuclear fire of the sun. And that creates a solar wind because this stuff just keeps going. Like it fades out here because the light of the sun doesn't illuminate it anymore, but that keeps going into space and blows all through the solar system. So we have that material passing us by in space all the time. And because Earth has a magnetic field, it catches that material as it's going past, and it funnels it down the magnetic field, and we get, we get another of one of the most beautiful sights in nature. Which may be turned off. Oh no, there it is. Of course, the magnetic pole is not quite aligned with the axial pole. We get the aurora borealis. The northern lights, or I think in this case the southern lights, because I think I'm at the South Pole, which look like this from the ground. And again, if I speed up time a little.
Is it also kind of true that, like, you know, all of the countries, we say, of the world, they're pretty much all kind of on one side of Earth?
Yeah.
And then if you turn it around, there's nothing on the other side.
Yeah.
Sort of. There's like, it's almost like one side is all the countries. Because I always think, you always think they go all the way around, but they don't.
Yeah.
They only go half the way around, and then the other half is just big blue, the big blue sea.
Indeed. And a very calm and Pacific one at that. Yeah, so we have Australia there, right? So I was on the southern lights. So I just upped the lighting a bit on the dark side and turned off the clouds. So here's what you're talking about.
Yeah, it's like, it's amazing.
Yeah.
It's just like a big bowl to me. It's like a big earthy.
Exactly, yeah. And that's...
Half of it's water and half of it, not even half of it, I suppose, is land.
No, indeed, a quarter would be land. Yeah, and also there's also a bias.
Are we living in heaven?
If your criteria is what's the best place for human life that we've seen in the universe.
Good answer.
We're already here.
Yeah.
Survive.
You go red.
There's a lot of colour, isn't there? I mean,
Oh, yeah.
The place we've been seeing is like white and black, you know what I mean? This is just blue and this green, you know, you've got
And that's
colour, like.
that's what's so wonderful about life.
Yeah.
Life does that.
Yeah.
We're here.
I have a question.
Yeah.
Why are there no triangular planets?
That's actually a really good one.
Thank you. If you can answer that, I'd be very happy.
So, that process I was talking about of stuff clumping
Magnitude
together.
and the circular motions and everything. It's all circular, everything's circular.
Yeah, but the actual physical mechanics of why things are round is in that process of the planet's formation. So it's pulling stuff in from every angle, right? And say, just by chance, there was more matter in 3 different directions, and it would logically form a triangle, right? But then you've got, especially, yeah, I'm sorry, I'm trying to think of how to express this. Then you've got essentially a planet with 3 enormously large mountains and no sort of flat land in between, so to speak. There are straight lines, but when you're on that planet, because the gravity is coming from the center of the planet, all of those would feel like slopes, except for the ones that are directly at 90 degrees to the core, directly perpendicular to the core. So that force of gravity is being felt by the material out of which those mountains are made as well, and so the stuff on the slopes of those mountains is going to want to roll down towards the point at which it doesn't feel that gravity anymore. So the point perpendicular to the core. So essentially, if you stack anything up too high on a large enough object, it'll get pulled back to roundness because of gravity. So it's gravity just kind of evening the
All force is circular.
Yeah.
excuse me?
All force is circular.
Yeah.
Bringing back to the solar wind.
Yes.
Again, is when the sun belches.
Yeah.
All the different elements then.
Yeah.
Do they? Because we're stardust,
Yes.
and is that why we are stardust?
It's close. It's similar. So the sun is putting out some of its internal material, but the reason that we're stardust, and this is a great segue for me to go and show you those nebulae I was talking about. I'll just return the lighting to normal. Turn on clouds. Okay. So the great thing about this is that this is both the beginning of a star's life cycle and the end, because stars are kind of cyclical. And I'll go and find a nebula for you now. If I can get up to speed fast enough. So there's a few out there. I'll just pick one at random, fly into it. There's one. Okay. So here we have, this type of nebula is often called a planetary nebula. That's kind of a misnomer. It was named that because when early astronomers were looking through the telescopes and they saw this circular thing, they went, well, it's another planet. But it's not a planet, really. I mean, it may be hundreds of millions of planets worth of material. But what that is made from, and actually there's a glowing remnant in the center there. So what happened here is there was a supernova. A star exploded at the end of its life. And what a star is doing while it's burning, and that fusion explosion that's constantly going on at its core is happening, is it's fusing elements into heavier elements. So it's taking hydrogen and oxygen and fusing them into water, H2O, and every other element on the periodic table. And as the star ages, it runs out of stocks of certain elements. And so it goes through different stages of its life cycle. And once it gets to the heaviest elements, the last stuff left to burn, it's a very inefficient burn. It swells up. It gets kind of an angry red. And then the reason, so a star is a big round ball because it's a constant explosion caused by the weight of gravity fusing stuff together at the center, and that explosion is pushing out against that gravitational force, and the balance is what keeps that explosion contained in a big round ball. When it runs out of fuel, gravity wins that contest, and all of the material of the star falls in on itself. And when it meets at the center, there is a titanic smash and a rebound. And the rebound creates the explosions that we know as supernova. There are a few different types of supernova, so that's not the only one, but that's the easiest to understand, and that's what happened here. So in the center we have what's left of that star, still kind of glowing with residual heat, and around here is most of that star thrown out into the universe. And all of this material is going to keep expanding out, and it may encounter wave fronts or shock waves, if you will. If this is a shock wave from another supernova, and that material will smack together, and that will create density knots in that material. Density knots being where the material is more concentrated. You get more gravity, pulls it in. You see where I'm going with this, you form another star. And so stars...
So we're the result of a massive explosion?
Yes, several, because multiple generations of stars died to make us. So all of that stuff there is everything that we're made of. It's the wood in this table. It's the flesh in my hand. It's the carbon and the calcium and the iron. Yeah, thank you. That make up our bodies. It's the silicon that makes up the floor. This is the makings of a solar system. And so that's why we're stardust. Yeah?
The amount of stability that we enjoy for the duration of time we've had it, the conditions we happen to have, for all these billions of stars, is there a likelihood of this sort of stability over billions of years existing in, I don't know what intelligent life might otherwise be, but
yeah,
some form of, some concept of that
absolutely
forming over, it's the billions of years that we've had it for.
Yeah.
likely elsewhere, or is it astonishing that we exist?
Well, it is astonishing that we exist, regardless. But stable situations are actually very common across the universe. Now, they may not be this situation, i.e., this temperature, this distance from the sun, this size of the moon, keeping us on a stable axial tilt, this much water on the surface, all of those, and the tectonic activity of the Earth, the shifting of the tectonic plates is thought to be a key factor for the evolution of life as well. And I just saw something, I didn't get to read it, but I saw something today about like mountain ranges are now being thought to be essential for life to have formed. I don't know what that's about. Anyway, stability is very common. And, you know, like look at the rings of Saturn. The scientific consensus keeps changing on how old they are and how long they've existed. But the youngest that I've heard them being dated at was 65 million years, which is a ridiculously long period of time for you and I, but it is also just the period of time since the dinosaurs went extinct, which were related to us, and so part of the tree of life on this planet. But yeah, stability is not uncommon. It's just what conditions pertain for that period of time is the question, and will they produce life? Yeah? Quarks.
Quarks.
Not my forte, unfortunately. Unless we're talking about Star Trek Deep Space Nine.
Yeah, no?
Yeah, not my forte. I'm not a particle physicist.
Not into the quarks.
Well, I mean, I love hearing
Atomic
about
orbit.
it.
Is it
Sorry?
the atomic orbit?
Yeah, I'm not a physicist of that degree. But what was your general question there? Oh, okay. Wrong person to ask, I'm afraid. I'm sorry.
Yeah, I have another question.
Yeah.
So tomorrow is supposed to be an eclipse. So, like, astronomically, what can you tell me about?
Okay. So, if I'm not mistaken, it's a lunar eclipse, right?
I think,
Yeah.
I'm not sure, solar.
Oh, solar eclipse. Okay, sorry. No, yeah, lunar. Sorry, I meant solar.
Yeah.
Honestly, I
So
did.
it's unusual maths, right?
Yes, yeah. So there is a weird coincidence about the relationship between how big the moon looks in our sky and how big the sun looks. The moon is 400 times smaller than the sun, and also 400 times closer than the sun. So when you put them side by side on the sky, they look exactly the same size, and that's a totally bizarre coincidence. So there's no, as far as I'm aware, there's no scientific theory as to why there might be some bias for that relationship to exist. So I can't account for that.
But it does make it kind of really meaningfully related because they're exactly the same.
It does, yeah. I mean, it is a bizarre coincidence because of how kind of spooky it is. So yeah, and it certainly fed into our mythologies and ideas about the heavens for. It is. It's stunning. And I didn't get to check if that's crossing Ireland. Did you hear if that's hitting us?
I think it's down the very bottom somewhere.
Ah, okay.
Yeah. It's visible from down there, but not kind of
Okay.
down the very bottom in the southern hemisphere somewhere.
I could actually fast forward to tomorrow and we can see where it lands.
I was just at a concert where we had a year in an hour or two.
Oh. Ah, well, you're an adept time traveler.
Yeah, exactly. We're in no time here. All time, no time.
So sometimes this program does get the eclipses wrong, but let's see. I think they've improved it. So
Brendan, would you like to take the last question?
yes.
Anybody else? Question? Last question?
I have one if you don't mind.
Yeah.
I'm going to need my notes for this one, sorry.
Okay.
I think we all know this question. Alright, so there are sailors fighting in the dance hall, Oh man, look at those cavemen go. It's the freakiest show. Is there life on Mars?
Excellent question. And excellent song. I was going to wear my other T-shirt, which had a red car in orbit of Earth, but anyway, possibly. So there are a number of probes on the surface of Mars active at the moment. A couple of them are rovers. The Curiosity rover, which landed in 2012, has been noting some anomalous methane emissions on Mars, and there are a couple of non-biological candidates for why methane would be appearing on Mars, but in the volumes that it's been detected, cows have been studied for a while, and the scientific consensus is that they are biological. But so there is still a tantalizing hint that there may be. There was another thing that I saw, a paleontologist was looking at the photographs being sent back by Curiosity, and NASA is extremely reticent to point to something and go, oh, that could be life, or that could be an indication of life, because they really want to nail it down. They don't want to get it wrong and have everybody be all excited, or indeed to then go to a lot of expense to sterilize a lot of tools to go in and check it out further, only to find out, no, it just looks like life, it's not life. But so paleontologists were looking at the pictures being sent back by Curiosity from like early on in the mission, and they were saying, if I was looking at these as field photos from like Death Valley in Utah, or some site that was relatively untouched back to the early days of life on Earth, like 3 billion years ago, I would be looking at these formations here and going, well, that looks like a microbial mat, which is like a colony of microbes that have formed together in a precursor to like moss behavior, and various other little formations that, while still ambiguous, could be fossilized evidence of life. But nothing has been confirmed yet. No discoveries are sufficiently unambiguous to say that there has been or is life on Mars.
Well, I also had, so our makeup and our whole matter has been created on Earth, right? So the way we perceive things, this is something that I find very strange, is that the way we see what happens on other planets, the matter and everything is so different that maybe there are actually dimensions that we just can't see because our eyes aren't actually, like, they're built on Earth.
Yeah.
So how can our Earth eyes see something that's actually happening in another atmosphere?
Yeah.
Because it's not the same matter. It's not happening the same way. So like there could be things happening that we just can't actually see and perceive with our human eyes.
Yeah, and there are processes that occur that emit wavelengths of light that are outside our visual field. We do have sensors and things that can detect most of those, but absolutely. Another thing to consider is like timescales.
Yeah.
If life evolved on the basis of silicon, based life, rocks, for example, or crystals that somehow became living, they might carry out their activities at a speed that we would consider glacial, and we may not even notice that it's a living thing because it's so incredibly slow to do things. Or it might be incredibly small, or it might be incredibly large and we pass it off as a mountain. That's one of the other issues. Yeah, but it's one of the other difficulties with searching for life, is like, what does life look like?
Yeah.
How do we even identify it if we see it? So I think with that, I will say thank you very much, everybody.
Thank you.
The Uncle Gold Podcast.